Welcome back. Today's background is House Vader. It's in a little town called Hakone-Yumoto, which is about an hour, maybe an hour and a half outside of Tokyo, and right next to a fairly famous national park where people like to do a lot of hiking and camping and stuff. It's a fairly typical Star Wars fan store. You can see Yoda there in the background, urging me on with my mad skills at Lagrangian mechanics. My t-shirt today is not from the shop. I had it before then, but it's full of some really interesting Star Wars stuff if you're ever passing by. And those of you who are ever in Tokyo looking for a tattoo-friendly onsen will know that they're as rare as hen's teeth. And there's actually one about 20 or 30 minutes walk down the road that way if you're ever looking for it. Okay, so to the third of the problems we're going to deal with today. This is a more difficult one. I'm going to include it because it's probably more an assignment question than an exam question, the way it's worded. As an exam, it would have to specify things a bit more tightly, but it's a really nice example of a problem where you really do need and want Lagrangian mechanics, and it's got some good aspects of equilibrium behavior in this as well. So let's specify the problem. We've got a circular hoop like so. It's got a bead threaded on it, so we can already see that there's a constraint to the motion. The bead is going to have to be required to be on the hoop. And then we take that hoop and we spin that hoop on its vertical axis with an angular frequency omega, okay? What's going to happen if you know a little bit of your physics is that as this thing spins around, there's going to be a gravitational force acting to drive this bead back to the bottom of the hoop, but due to the spinning, there's going to be a centrifugal force that pushes it up. Some of you will be going, hang on, we got told there's no such thing as a centrifugal force in high school, blah, blah, blah. We'll deal with that in a couple of lectures from now when we do rotating reference frames, and you'll see that centrifugal force is basically a fictitious counterpoint to centripetal force that pops out when you deal with rotating systems. So it's going to be acting to drive this thing up, and you're going to get a balance between the two, and the bead's going to sit in various positions in this problem, okay? Got a specified radius, an angle that runs up from the bottom, so this would be 0, this would be pi, and then we've got an extra variable in here, rho, that you'll see later on is actually quite common if you're dealing with sort of spherical systems. Often you're less interested in how far you are away from the center and more what your closest proximity to the rotational axis is, and that's often called rho in these problems. Okay, so first things first, let's get into degrees of freedom and constraints. Sometimes I handle these together because it makes sense to do so. What we're going to have here is basically the bead is constrained to stay on the hoop. So that's one constraint. We could write a constraint equation for it, but it's not very useful in this problem, so we won't. And then there's, in principle, 3 dimensions that we have to worry about for the bead. And 2 of them are constrained by being on the hoop, sort of an XY plane. And the other one is sort of taken care of by symmetry. With this hoop rotating, you can imagine that no matter where you look at the problem in the rotation, the problem's kind of going to always look the same, right? You've got this constraint in the plane of the hoop that takes care of 2 of the dimensions, and then you've got a third one. One way to think about this would be to have a frame of reference that's rotating with the hoop, and that's where later on we'll see this centrifugal force comes from. For the moment, we can just imagine that there's a symmetry in this problem that means that as far as understanding what's happening with the bead is concerned, there's only 1 degree of freedom, which is its ability to move around this hoop, and that is tied entirely to the angle, so there's 1 degree of freedom, okay? So in this problem, we've got degree of freedom equals 1. We're going to deal with theta in the problem, okay? The next step here will be to deal with Lagrangian. The kinetic energy is pretty straightforward. We'll come to that in a second, but we're going to have a potential energy term that's gravitational, and so we're going to need a height. So I'm going to draw a little bit of an extension of this diagram I have in here, and I'm not going to draw the whole thing, partly to save some time and partly because my ability to draw freehand circles is just horrific. So we can imagine you've got the bottom of the hoop there and it goes up around here, and that's as much as I'm going to draw. You can already see it's a terrible circle. And this is R, this is rho here, this is theta on the axis. And what we're going to be interested in for gravitational perspective is our height above the lowest height that we can get. Okay, so this would be our h just here. We know that this is R, And we know that this length here is going to be given by trig, and since this vertical is the adjacent to the angle, this one here is going to be r cos theta, and this one here is going to be r sine theta. Okay, dealing with all the trig right up the front of the problem. Okay, so first thing we have to deal with is kinetic energy, and our kinetic energy term has two components in it. One is a radial component of the bead around that ring, right? So we can write here a V of theta is equal to R theta dot. And then the other one is going to come about because the bead, it can't move radially, so we don't have to worry about that component. We have to worry about the component around the spinning motion of the hoop, right? And so this is where the diagram comes in handy here. You can imagine this hoop, this bead spinning around in a circle here with angular frequency omega and a radius about the axis of rotation of rho. And so our velocity in the omega direction is just going to be rho omega, which is r sine theta omega, okay? We can build all this together to get our t. So our t here is going to be a half m. When we take the square of the velocity, we're going to get a common term of r squared out the front. And the top one will give us a theta dot squared, and the bottom one will give us an omega squared sine squared theta. Okay, and so that's our kinetic energy term right there. Next thing we have to deal with is our potential energy, and we know that it's mgh, and we need an expression for h. So h is going to be this distance here, r minus this distance here above h. So it's going to be r minus r cos theta. And so we can take our u here and write it as mg. We can isolate r as a common term, 1 minus cos theta. Okay, so moving right along here, we can write our Lagrangian as t minus u. So it's going to be a half m r squared theta dot squared plus omega squared sine squared theta. Close brackets just there. Minus mgr 1 minus cos theta in here. Okay, so two quick observations. One, you'll notice that I wrote L equals T minus U up above. I've put that in because there's two things that could go wrong in the big long line I just wrote. One could be that I made a typo, and if I didn't specify what L was, it could be easily made that I didn't just make a typo, but I didn't know what the Lagrangian was, right? Imagine the minus sign in the middle was a plus, then I might be thinking that it's the total energy and I've got my things wrong, okay? So this is just a little bit of exam technique. For extra 4 strokes of the pen, I can kind of ensure myself against some examiner thinking that I don't know what the Lagrangian is. If I make a typo on the next line, they just know I made a typo. And from a marking perspective, there's a difference between a typographical error and not knowing something, okay? So just a little technique thing there. And the other thing to spot just here is that there's a little constant term in here that's going to vanish, okay, when I take derivatives. And it's good to know that that's an error so we can handle it when it comes up. Okay, so the next step would be to do our Euler-Lagrange equations. And there's only one in this particular case. So we've got dl on d theta equals d on dt, dl on d theta dot. And again, it's a few pen strokes just to make it clear that I know what I'm dealing with on the next step, so that if I make any mistakes down below, it's clear that I came from the right starting position. So I've got dl on d theta, and you can think about this in two particular ways here, right? The term that we have to deal with for this is this one and this one. And this one here has a sine squared theta in it, okay? So there's two ways to do this. One is to remember and I hate memorizing things, but to remember that the derivative of sine squared theta is 2 sine theta cos theta. The other way to think about it is as the product of sine theta and sine theta, and then you just use your product rule. So it's going to be the derivative of the first term times the second, plus the derivative of the second term times the first. When you do that, the sine, one of the sines becomes a cos, you get 2 sine cos theta, okay? It knocks out the half on the front, so this will be mr squared omega squared sine theta cos theta. And then the term hanging on the end here is going to be mgr, and of course our cos will become a minus, and it will knock out the minus that's already in front of it, so we get a sine theta just here, okay? And then dl on d theta dot is pretty easy in here. It's just this term hanging off the front, and so it will be mr squared theta dot. And then I'm going to do this slightly different flavor just to show you that these things are all equivalent. I could then work out what this other derivative is in here, okay? This is equally a valid approach. D theta dot, and of course it's going to be m's constant, r's constant, theta dot becomes a second derivative in there, okay? It's the only thing that's differentiable. Okay, and so now what we can do is pull our Euler-Lagrange equation together. So we're going to get mr squared omega squared sine theta cos theta minus mgr sine theta is equal to mr squared theta double dot. Okay. Thing to do regularly in problems is to look for common terms and knock them out. And the obvious thing to get rid of here is the mr squared. We have to be a little bit cautious because this does not have an mr squared, so we need to correct for the missing r in there, okay? So this thing's going to end up, I can flip the two sides, get the theta double dot out the front. Theta double dot is going to be omega squared cos theta minus g on r sine theta in here. Okay, let's call this equation 1 because it's kind of our final writing of our equation of motion just here. Okay, and you'll notice there's a common factor of sine theta, so I've pulled it out of as well, but I can't make it go away because it wasn't on the right hand side. Okay, you can substitute back and you'll find that it's all hunky-dory. Okay, so someone in the forums asked me, you know, what happens if we get an equation in this that's, you know, something that's non-integrable or an equation we can't solve or whatever. Yeah, that happens a lot in physics, actually. And so immediately you would go here, okay, this is just a second order ODE. And you would go, okay, well, how am I going to solve this thing? And the interesting thing is, it turns out here that this particular equation can't be solved analytically. You might be able to do it with sort of numerical methods. You can possibly kind of do it with some rather advanced functions, but at least just in terms of elementary solving DEs, this one's just an intractable problem. So in a lot of cases like this, and this is probably one of the interesting aspects of higher year physics, particularly when you get to third year and fourth year, is you start to learn that not all problems are solvable, and you start to learn which ones are and which ones aren't. And for the ones that aren't, the tricks that you can use in such a way that a problem not being solvable doesn't mean that you just give up and walk away, but you kind of get somewhere, okay? And this is really one of those problems, okay? The clue is kind of hiding in the question at this point, which is to say, find any equilibrium positions at which the bead can remain with theta constant, okay? The can remain here is pointing to the fact that it's interested in stable equilibrium points. With this an exam question, it would be specified in specific words, but as an assignment problem to make you think about what's required, it's perfectly fair game. And so the thing we know about equilibrium positions is when you're in an equilibrium position, your position is constant, your velocity is 0, and you're remaining at that position, so your acceleration is 0 as well. And the equation of motion that we just got is for theta double dot, which is the acceleration, and that will be 0 at the equilibrium points. So the fact that in this problem we're interested in a limited part of the dynamics means that we can actually still solve the problem despite the fact that we can't solve the equation of motion to get all of the dynamics of the problem out very easily, okay? So what we really need here is for theta double dot to be equal to 0 at equilibrium. And really what's that saying is that omega squared cos theta minus g on r sine theta is equal to 0. And that's a much easier prospect to solve, right? As we all know, there's two ways that this can happen. The first way that this can happen is, let's call this A, is that sine theta is equal to 0, right? And this is kind of the easy solutions. We all know what this is. Theta is equal to 0 or pi, okay? So basically what we're saying is one of the solutions, one of the equilibrium points here is the bead sitting at the bottom, and the other equilibrium point is the bead sitting at the top. There's another solution in here, B, which is that omega squared cos theta minus g on r is equal to 0, okay? And here we can isolate the one variable, which is theta. And so we can go cos theta is equal to g on r omega squared. And there's two things we can do to handle this, right? The first is we could just go straight to theta. So theta is going to be cos of minus 1 g on r omega squared. The other is to realize that cosine is a constrained function, right? So, for example, if you think about cosine, it can never be bigger than plus 1, and it can never be bigger than minus 1, right? That's what we mean by a constrained function. You can put an argument in and it will never stray beyond certain values in terms of what the function comes out as. And so what we've got here is the absolute value of cos theta must be less than or equal to 1, right? We know that's going to be true. Cos is between plus 1 and minus 1. With that being the case, we know that g on r omega squared must be less than or equal to 1. Okay, we just draw a line here so that it's obvious they're separate lines of logic. And what that means is we can now pull this out in terms of a variable we can control versus something that's a fixed of the system, right? So this would be omega squared must be greater than or equal to g on r, okay? So what's happening here? If omega squared is greater than g on r, then cos of theta is inside 1, and so we can have an allowed solution to our problem. If omega squared is smaller than g on r, then cos of theta would be outside plus or minus 1, and so we can't have a solution, right? So what this is telling us is that this is okay only if omega squared is greater than or equal to g on r. So we basically have a pair of equilibrium points that appear when omega gets fast enough, okay? There's another thing to realize here as well, which is that there's a symmetry inherent to the cos function about theta equals 0. And so we actually need to consider plus and minus in this particular case, okay? And this basically corresponds to one equilibrium position being here and one equilibrium position being here. And they're kind of the same thing, right? Because if you rotate the hoop by 180 degrees, they sort of swap for each other. So in terms of handling them, you can treat one as equivalent to the other, but both of those solutions exist, right? The bead could go up that side, and you could make them, you know, a black end and a red end, and the black end is distinct from the red end, so we have to treat that as a solution that's in there. Okay, so another one of those things to think about when you solve these problems is, you know, do I have to include a plus or minus? How many solutions can I have? All these sorts of things are sort of whirring around inside my head while I'm trying to solve problems like this. Okay, so now we can sort of categorize all these solutions together, and we've got something that looks a little bit like this. We've got two solutions, one at 0 and one at pi. They always exist, right, as equilibrium positions. And then we've got two here that appear partway up the hoop, and they only exist when it spins fast enough, right? Okay, so the interesting thing to do here, particularly in light of the question, is it asks equilibrium positions at which the bead can remain with constant theta, okay? And the word remain is kind of a trigger for asking about stable and unstable equilibriums, because as you know, if you have an unstable equilibrium, you almost never stay there because it's almost impossible to get right to that perfect unstable equilibrium point where you actually do balance. And the slightest perturbation will kick it off, right? So what the question's really asking here is, where are the stable equilibrium points? And the thing we know is that if we take a stable equilibrium and we push away from it, the acceleration will try to drive us back to the equilibrium point. Whereas if it's unstable, if we drive away, the acceleration will drive us further around, okay? So the next step in this question is basically to characterize the equilibrium points. And I'm going to use my numbering that I've got in the diagram here. So let's treat the one at the bottom. And the way I'm going to do this is the one at the bottom I'm going to do in a little bit of detail so you can see the logic. The one at the top I'm just going to argue my way out of because it's kind of obvious. You can do the equivalent maths for it yourself and find that it's consistent, but there's a quick way to explain what's going on. And one of the nice things in physics is that often you can save yourself some maths by an obvious explanation. And then the two on the side, what I'm going to do is not do them in full mathematical detail. I'm going to argue why they behave the way they behave, and I'm going to leave it as an exercise for you to actually just work out exactly what's going on there, okay? So the one at the bottom is going to be theta equals 0. And if we move away from equilibrium, what we're really doing is saying that theta is going to be small, okay? So for theta small, we know two things. First, we know that cos theta is roughly equal to 1. And the other thing we know is that sine theta is roughly equal to theta, okay? And so what we can do is take our equation of motion and rewrite it with those two things in mind. And what we'll find here is that theta double dot is equal to omega squared minus g on r. The cos term that is behind the, where's my equation? It's just up here. Let me highlight it so I can come back up to it sometimes. The cos term that's in here is going to be 1, so you can see that that's vanished just in here. And then the sine term on the end is going to become theta, so I'm going to write a theta on the end of this, okay? All right, now here we can spot that we're going to end up with two cases, so we should split them off, right? We're going to have one case where omega squared is greater than g on r. And we're going to have a case here of omega squared is less than g on r. And the equality case, you'll realize, is a bounding condition, okay? We'll put some meaning to that later. If omega squared is greater than g on r, then we're in the case where the ring is spinning very fast, okay? And I'd rather not deal with that one first, so I'm actually going to deal with this one. The physics makes more sense. So let's deal with this one. Omega squared is less than g on r. So there what's going to happen is that this number here, omega squared minus g on r, is going to be less than 0. In other words, it's a negative number, okay? And so what we could really say here is that theta double dot is equal to a negative number times theta, okay? So let's think about what the implications of that are for our equilibrium. If we take theta and we go positive, now we've got a positive deflection times a negative number, which is negative. So theta double dot is negative, which pushes it back towards 0, okay? And if we take our deflection negative, so theta is negative, negative times negative is positive, theta double dot is positive, it pushes back towards the equilibrium point. So that one's stable. All good, okay? And we can understand what's going on there. Basically, gravity's driving it back to the bottom, and the centrifugal force isn't strong enough yet to drive it up the sides because the hoop's not spinning fast enough, okay? Let's come to this second case, which is now hoop spinning very, very quickly. Omega squared minus g on r here is now obviously greater than 0, so it's a positive number. And so what we've got is theta double dot is equal to positive times theta. And if we think about what happens here, now if you imagine theta goes positive, theta double dot is a positive number times a positive number, so it's positive, so it drives the deflection even more, and this thing just out of there, right? And you can think about the same thing on the negative side. You've got a deflection that's negative, so go that way. So no, go this way. You've got a deflection that's negative, and your leading number is positive, so minus times positive is minus. The acceleration is directed in the negative direction, it drives it out this way. Okay, so this is now an unstable equilibrium. And so what's going on here is we've got a transition in this bottom equilibrium point such that it goes from being stable at low angular momentum to unstable at higher angular momentum. And that's basically a crossover in the balance between the gravitational force driving it down and the centrifugal force driving it up, okay? All right, so we understand what's going on there. Number 3, we can deal with here just by waving our hands around a little bit. If you think about what's happening at the top, gravity is going to make that an unstable equilibrium, right? Automatically. And then centrifugal force is going to act away from that point as well. And it's only going to make it less stable, not more stable. So that's always going to be an unstable equilibrium at the top, okay? Perfectly satisfactory explanation without getting into the maths. That's an unstable equilibrium, obviously. You can go through and look at what happens with sine and cos for yourself and make your arguments of positive negatives, and you'll find that that's consistent, okay? And then we need to deal with the second solution in here, number 2. And to do this, I want to bring back my equation from before. So it's theta double dot equals omega squared cos theta minus g on r sine theta. And let me just pop back up and check that's right. Yep, good. Okay, my memory's not getting terrible. Okay, so this one is a bit trickier to argue, so I'm going to let you work through it in a little slower detail later with my notes, but there's 2 really important things that you have to think about when you think about this solution, right? So first, let's draw a graph down here for a second of theta and a function, right? And this is our position pi on 2 here, right? Cos will go from being 1 at 0 down to 0 at pi on 2, okay? So this is cos. It's a decreasing function as a function of theta. And then sine will go from 0 up towards its maximum of 1 at pi on 2, okay? So this one is sine. The other thing to keep in mind here is that the equilibrium point here corresponds to this thing being equal to 0, right? Because it's the piece that we made 0 in order to get that equilibrium point. So when we're at that equilibrium point where theta is somewhere between 0 and 90 degrees, which is why I've only drawn sine and cos over that range, we need to think about what happens as we work our way through that, right? So if we make theta more positive, then what will happen in here is that our cos theta will become smaller, right? Because cos is a decreasing function of theta. And so this cos becomes smaller, which makes this term on the front become smaller, which drives this overall term here negative, right? Omega squared cos theta becomes smaller than g squared on r, so it becomes negative. Sine remains positive, right? All over this range. So it's a negative times a positive. And so we end up with a negative that drives us back towards that equilibrium point. If you think about the opposite direction of this, of making our term here more negative, what happens is we make theta smaller. Our cos theta will become bigger because we're heading back towards this axis here. Omega squared cos theta up the front here will become bigger, minus something that's a little bit smaller, so that number becomes positive. And the sine theta is a positive function, so it's a positive as well. So we've got a positive contribution there, which drives us back towards that equilibrium point, okay? So we have acceleration that goes negative on this side, positive on that side, drives us back towards the middle. So this is obviously a stable equilibrium, okay? Realize I went through that one pretty quickly, so you might want to take your time and slow that one down, walk through step by step, but the logic is there, okay, just to keep the video somewhat contained. And so the final case we've got in this problem, just to sum up, is we've got omega squared less than g on r and omega squared greater than g on r. And in these two situations, we've got our equilibrium point 1 is stable and 2 doesn't exist because it violates constrained range on cos. And then when we cross over that, our solution 1 becomes unstable and our 2 becomes our stable solutions, right? And the interesting thing is what happens at omega equals g on r. And so if you think about what happens with the angle where the equilibrium point is as a function of omega, what happens is it actually starts right at the bottom where the point 1 is, and then spreads outwards symmetrically about that bottom point once omega becomes bigger than square root g on r, okay? And so what we have here is a thing in physics that we call a bifurcation. We have one stable point that at some point becomes two stable equilibria that then separate from each other, okay? And so we won't have time to do chaos in this course, I don't think, but you may see it later on in your studies. You'll see diagrams like this turning up all the time in chaotic dynamics books. Often they're on the cover because they're interesting diagrams. And you can see here exactly this, a bifurcation. So you've got one stable equilibrium point here that suddenly comes to a point where it splits into two and diverges, and you can have that going again and again and again in a system, and you get some interesting dynamics coming out, okay? So one of the reasons why this problem is interesting, not just to demonstrate Lagrange mechanics techniques, is also that it's one of the first places in physics where you see a bifurcation turn up. It also turns out to be a very interesting problem. A lot of people ask me, oh, you know, that's kind of cute, but what's it for? So the mechanics that we just did in this third problem is actually underpins a really important engineering invention of the past.
A centrifugal governor is a device used for controlling the speed at which a machine operates by regulating the admission of working fluid. Invented by James Watt in 1788, the governor became a fundamental component in many of the machines that drove the Industrial Revolution. Most commonly fitted on steam engines, power is supplied to the governor via a belt and flywheel connection with the engine's output shaft, causing the governor to spin as the engine runs. The governor operates the throttle valve, supplying steam to the cylinders. As it spins with greater speed, the centrifugal force acting on the fly balls causes them to move outwards and upwards against gravity, pulling the lever arms with them. As the lever arms flex, they pull down on a vertical shaft, lowering it into the throttle valve and reducing the gap through which the steam is fed. If the governor spins fast enough, the shaft cuts off the steam intake completely. The utilization of a governor became crucial in the operation of large engines and machinery during the Industrial Revolution, and long since. If an engine is allowed to run too vigorously, it runs the risk of shaking itself apart. Furthermore, in large factories where a multitude of identical machines were configured to run off of a single engine, as the power looms in a textile mill, a constant, steady, and stable speed had to be maintained at all times, or the work produced would be irregular. There are numerous examples of centrifugal governors to be found in the museum, designed to be fitted to steam engines and water turbines. Though differing in size and complexity, each one is an equally crucial component of its machine.
It might seem like steam engines are a thing of the deep dark past, but you can imagine using that sort of concept in other places. So you might have the two solution points on this actually connected to a lever that activates when you hit a certain speed and it cuts out when you have another. So you could have something that basically acts to constrain velocity of your system with a sort of two end triggers on it. And you can imagine taking this to other places. So there's lots of things where gravity and orbital or rotational dynamics are really important. And so to give you one example, at the moment, one of the really edgy things to do is to build microsatellites and put them up into space, okay? And so you can imagine having to worry about the interaction between gravity and rotation in very similar way to the problem that we've got here in some of the problems that you deal with there. Okay, so a lot of these are really interesting engineering problems. And for any of you who've read Station 11, you might realise that one day, with recent pandemics and near civil wars in countries and all sorts of things, we might go back to the day where steam engines become important again, and having skills for making steam engine governors might be a really useful thing to do. Okay, so I'm going to finish there. We've now done a stack of Lagrangian problems, everything from really trivial ones we did in previous lectures to some of the really complicated ones that we've done today that almost get beyond exams to assignment problems. And we'll change topic slightly from next lecture, but hopefully today's examples have been useful. See you next time.